Thank you very much for the introduction. Thanks to the organizers for inviting me, for giving me the opportunity to speak here. I'm particularly happy that Michael Hoffman is chairing this session because, as some of you might know, he's maintaining a really long list of all sorts of papers in multiple zeta values, multiple harmonic sums, and recently there's a new section which is called Elliptic multiple zeta values. And I think, I don't want to boast, but I think maybe half of the papers are written or co-authored by me, so I'm very happy that Mike is chairing this afternoon session. Okay, so first a disclaimer. So this talk is going to be a bit on the concrete side. So this means I'll be talking about periods, but the motives behind these periods I will not talk about much. So I want to stay somehow concrete, and it would take me a bit too long if I were to talk at length about the motives behind it. And I'll start with the introduction. Right, that's the plan. The introduction. I'll talk about a specific example, which I hope is well known to the majority of people, but I'll give some detail. And then I'm going to talk about what I really would like to talk about, the elliptic curve case, elliptic multiple zeta values. So the general setup is as follows. I'll be very general, and then I'll become more concrete and more specific. So X will be a smooth, and in the applications that I'm going to present, it will always be affine curve over the complex numbers. And then there's two things you can look at. Classically, you look at integrals. You look at integrals, and what does this mean? You're looking at expressions. Integral some smooth one form omega along some piecewise smooth path gamma. That's going to be a complex number. So omega smooth one form, and gamma a piecewise smooth. Right, so very general. Of course, if you're interested in periods, then you might want that omega and gamma are defined over Q or algebraic over Q in this dual sense, but we can be more general. And then the one point I would like to draw your attention on is if you have two loops, gamma 1 and gamma 2, say based at the same point, little x and capital X, then you have the following elementary formula. If you take the integral of omega and now you integrate in the group ring, kind of, so in your then by linearity you can take this apart and you're getting, let's just do it, you're getting something like this. So integral gamma 1, gamma 2, integral over gamma 1, integral over gamma 2, and the integral over the trivial path, and this gives you 0. So what does this tell you, kind of, is that integrals, so I like to think of this as that integrals are inherently abelian. That is, they don't see elements in the commutator of the fundamental group. Jumping a bit ahead, I haven't talked about classes of paths. And in particular, they do not depend on the base point. So they do not depend on base point. On the other hand, if you want to look at iterated integrals, so what are iterated integrals? So now you don't just have one smooth one form, but you have a whole collection of smooth one forms. You still have one path gamma, and you have smooth one forms omega 1 to omega s. And what do I mean by this? It's defined to be, take the integral over a simplex. I'm going to order it in a slightly non-standard way. 1 greater or equal t1, greater or equal and so on up to ts, greater or equal than 0. And you pull back the forms along the path gamma, and that's again going to give you a complex number, and again the omega I are smooth one forms. Now the corresponding property of the second one here, the second bullet point here, is if you now have paths gamma 1 up to gamma r, and r is greater than s. So you have more paths than forms, and they're all based, okay, they're all based at the same point again, so all based at some point little x and x, and r is greater than s, then you have a corresponding property. If you now take the iterated integral omega 1 omega s, but now over a product gamma 1 minus 1 up to gamma r minus 1, that will also be 0. But in general, if r is smaller or equal than s, then you will not expect such a thing to happen. And so the way to think about this is that iterated integrals are kind of non-abelian. So they really enable you to see elements in the commutator. And a more precise way of saying non-abelian, so this is just for the experts, I will not explain what I mean by this, is they're pro-unipotent. And in particular, they really depend on the base point. And the study of integrals is kind of classical, and my talk will be about this, the right-hand side here, class of iterated integrals on an elliptic curve. Okay, so I'm push this up. And okay, I can't really avoid writing in the dark, can I? No. Okay, sorry.
You can raise it up a little bit.
I can raise it a little bit more.
No,
The bottom one.
Oh, the bottom one.
It'll still be in the dark.
no, up.
Up. Well, then it's even more in the dark.
Yeah,
But at least it's visible.
But the guy.
Oh, great. right. Yeah, thank you. Right, so now I want to talk about P1 minus 3 points and multiple zeta values. So now x will be P1 minus 3 points, which I really mean spectrum of a polynomial algebra in z, z inverse, and z minus 1 inverse. Right? So you see now we're already much more algebraic, much closer to periods. Then we have two things we can consider. We can consider Durand cohomology, say algebraic Durand cohomology of x with coefficients in Q. And as we've seen in Francis' talk, and probably in some other talks as well, this is a two-dimensional vector space spanned by the classes of differential forms omega 0 and omega 1. And let me put this here, omega k is dz over z minus k, for k either 0 or 1. So this gives us the differential forms we're interested in. And now I want to think about the paths, so let's look at the topological fundamental group. Some base point x chosen, I'll be more specific later on. So this is a non-canonically free group on two generators, called gamma 0 and gamma 1. And the picture you should think about is you have puncture 0 here, then you have a loop going around like this. So say our base point is kind of close to 1/2. You have 1 here, and then you have another path gamma 1 here. And by Cauchy's theorem, the integral omega k along gamma j is equal to 2 pi I if the indices match. So this is just a special case of Cauchy's integral formula. So this gives you the portion on the left, so the integrals on P1 minus 3 points. This is kind of what it is. But then I want to talk about iterated integrals. And what do we have here? Well, so the idea is you take the exact same differential forms, but so it's going to be non-abelian, so we also add a x0, x1. Okay, so I'm sorry, this should not be confused with, maybe I should call them, yeah, x0 and x1 is fine, but they're not going to be base points, they're going to be formal variables, non-commuting. And I'm going to look at the following connection, nabla kz. So kz here stands for Knizhnik and Zamolodchikov. And the kz connection is given in the following way. It's d, the differential, minus the connection form capital omega kz, where capital omega kz is a one form taking values in the formal variables, and it's omega 0 times x0 plus omega 1 times x1. So this is just a connection which probably is immediate. First thing you think about if you think about p1 minus 3 points. But what is really crucial is, what's really important to have in mind and to really know is that this connection is flat. So its curvature vanishes. And because of that, we can consider the monodromy. Take the monodromy not just along a path, but along a homotopy class of paths. So gamma is now going to be a homotopy class of paths, and it's going to be paths from x to y. So you see I'm thinking from right to left, kind of. So it's paths from x to y. So gamma is a homotopy class of paths from x to y. And concretely, so how does this look like? Push that up again. Concretely, what you do is you take all powers of your connection form and you integrate along the path gamma you're considering, and this is going to give you a formal power series in these non-commuting variables x0 and x1. So this is formal power series with C coefficients. All right, so yeah. Okay, don't erase the chair. But other than that, everything. So remember, so I just erased it, but remember that in the iterated integral story, the base point is somehow important, and you really get different answers depending on what base point you're taking. So and here, so I want to take base points, and they should have somehow good reduction over the integers. And this forces you to work with, so this narrows it down to just 6 possibilities, and in particular it forces you to work with so-called tangential base points. So you've got to take plus or minus the tangent vector 1, point z, so this is in the tangent space, point z of the compact curve, so just p1. And z is either 0, 1, or infinity. The idea is the base point should not collide modulo any prime number with one punctures and should be non-zero in particular, so then you only have plus or minus 1. Okay, and we're going to look at, in fact, we're going to look at 0, 1, so we have the base point. Maybe I can use a different color now. So this here's the base point 1 at 0, and here we have the base point minus 1, 1. And at least when you're French, this is called the DCH, and it stands for droit chemin. So I'm not French, but I still like to call it that way. The droit chemin, so this is the straight line path from 0 to 1. And we want to take the monodromy of the Knizhnik Zamolodchikov connection along this path. And there's a slight hassle to do this because the connection has singularities at 0 and 1, but they're rather of a mild type. They are logarithmic singularities. So the option is you can really do this. You can take the regularized monodromy along this path, and you get something that's usually called phi, x0, x1. So yeah, copying what I had before, it's just the monodromy. This path, that's going to be a full power series again, and that's what's usually called the Drinfeld associator. Well, that is the Drinfeld associator. Yeah, and we had so in Leila's talk, for example, I think we've already seen the Drinfeld associator. And well, the important thing kind of is that to connect with multiple zeta values, the coefficients are Q linear combinations of multiple zeta values, MDVs. So they will not play any role, but let me still write them down. These numbers, zeta k1, kn, equal to the sum m1 greater than m2 greater than mn greater than 0. And then this is the expression you sum over, and k1 should be at least 2, and all the other indices should be at least 1. Okay, 2 little remarks before I go on to the elliptic side. Because it's kind of a workshop on regulators, so I thought that let's see where they come in. So generally, if you have a word in x0 and x1, then you have a notion of depth. And the depth of a word is just the number of x1s occurring in that word. And then one can show that the Drinfeld associator looks like this. You have 1 minus an infinite sum, n equals 2 to infinity, zeta, or let me call this k maybe, k. And then, okay, we're in the non-commutative full power series, so we can consider the adjoint action. We take the kth power of the adjoint action, or the k minus first power of the adjoint action, x0 acting on x1, and then we're getting terms of higher depth. And this is where the regulators come in. So kind of these are regulators of the rational numbers, right, or of the integers. And so you see in the depth 1 part of the Drinfeld associator, we're getting the regulators. So this is where they come up. And this was, I think, so I learned this from, so there's this 1986 paper by Deligne on P1 minus 3 points. And in the introduction, he says that it was inspired by some computations made by Wojtkowiak. So I'm going to give the credit to them. And secondly, there's also a motivic version. There also exists a motivic version of the Drinfeld associator, and it came up in, which is in some sense a bit, just in some sense more structure. It's a bit easier to work with, and that came up in Brown's talk, I think. Any questions at this point? Because I will go elliptic soon, and also ask while I erase if there's anything. No questions, so then we go elliptic. So I would like to start by coming back to Decane's talk on Monday. So there he made the point that if you have P1 minus 3 points, it plays kind of an ambiguous role. So P1 minus 3 points is at the same time the universal hyperbolic curve with genus 0. Well, let's say genus 0 curve with 3 points removed. So it's sometimes it's a universal curve over M03, which is spec Z. And on the other hand, it's also the moduli space of genus 0 curves with 4 marked points. And in his talk, when he talked about genus 1, he was generalizing it to the M11, and then you have the moduli space of elliptic curves. And this was his talk, and what we are going to do is we're more going to think of P1 minus 3 points as a single curve with 3 points removed. And so accordingly, we're going to look at an elliptic curve. But the things we're doing will have a nice modular interpretation, so they will depend on the parameter, and everything will be nice. So we start with tau. It's just a coordinate on the upper half plane. First, it's going to be a point in the upper half plane. And we're going to consider the associated once-punctured elliptic curve. I'm really thinking complex analytically here. With coordinate psi, it's going to be r tau plus s. And r and s be real numbers, but I gotta take out the integer lattice because I've taken out 0. And okay, and we're going to make the same considerations as before. So we're going to look at, first of all, we're going to look at the cohomology. So yeah, I think I'm really kind of taking C infinity to round cohomology here. So say complex coefficients. This is again two-dimensional, and it's spanned by the classes of d psi. And so this is a differential of the first kind. It's holomorphic. And then you got to choose something else, and I will choose for this talk. I'm going to choose dr, so this is kind of dual to the tau coordinate in the coordinate here. Of course, you can make other choices if you wanted to, and I will come back later to this point. You have to make a choice here. right? So that's the de Rham cohomology. Let's say de Rham. And what about the fundamental group? Again, any base point rho here. And it's going to be a free group again on two generators, alpha and beta. And so I think for this talk I'm going to think of an elliptic curve as something like this. So the fundamental domain and right, and then I have a base point rho, let's say it's here. So okay, and then I have let's see, does screenshot work? I hope. So that's what I call beta. And then that's alpha, right? Okay, and I will not talk about integrals on the elliptic curve. I'm going to jump straight ahead to iterated integrals. And okay, so what do? We want to have an analog of the Knizhnik Zamolodchikov connection on the once-punctured elliptic curve. So, and we're going to do a thing first that is not going to work. Okay? But we call this nabla KZB naive. So naively you might say, okay, for KZB, that's Knizhnik Zamolodchikov and this is Bernard. And naively you could say, okay, I just take my basis of the de Rham cohomology as I did before, and I'm going to consider this. Together with, again, with formal variables, A, and okay, let me put a 2 pi I here, I'm going to put it later on anyway, B, where again A, B are formal variables, non-commuting. And why is this naive? Was there?
Well, if you answer the question.
Okay. Okay, right, okay. Yeah, please, audience participation is great. No,
So I'm confused about something. You've got A going with DR.
all right, yeah.
R is, so it's your alpha.
Yeah, this is,
Is it the other way around, alpha and beta?
yeah, it's the other way around. I also realized when I wrote the notes yesterday, but
That's fine.
it's so ingrained in my thinking that, but right, I mean, DR is really dual to what you would call beta.
That's fine.
But the comment I was going to make is that's not a flat connection.
That's exactly the comment that I wanted to make. This is why I called it naive, exactly, yeah. You're completely right. This is, the curvature is not going to vanish. And the problem really is that we have a non-holomorphic differential here. So the curvature equation is somehow d omega minus omega wedge omega, and d omega is going to vanish because d psi and d are closed forms. But the wedge product of a, I mean, this is a holomorphic form, and here we have 0-1 form somehow. This is not going to vanish. So one has to do something, and I will not tell you why you do what you do, but I'll just tell you what you can do, what you should do. And this is the real, the non-naive KZD connection. So there's variance. You can do many slightly different things. And what I will do is, so yeah, I should maybe say before I go on. So there's a, I have to state my intellectual debt here. So many people have worked on this. So Brown Levin, they never really use explicitly the term KZD connection, but it's somewhat implicit there. There's Kalak and Enriquez setting off. There's also some important work by Decane on this, clarifying, also particularly considering algebraic aspects of the KZD connection, and also Levin and Racinet. And perhaps there's even more people, I guess, but I'm not so sure who else. But Certainly these were the ones which influenced my point of view in this KZV connection. And omega KZV, and here's where I'll follow Brown Levin, is going to look as follows. So we have dr times a and plus 2 pi I, and now it's going to be a bit messy, a bit long. So we have the adjoint action of a exponential r, so remember r was the part of the coordinate, at a, and then comes the main hero is really this guy, f tau 2 pi I xi. It's going to be a formal power series in the second variable, and I can put the adjoint action here, acting on b, and okay, I'm terribly sorry, I have to squeeze somehow a d xi in here. Let me do it like this, running out of space here. So there's a d xi there, so I want to consider this as a differential form. And f tau is a function of two variables, so we have the fixed parameter tau here, and we have xi and eta, and this is what's often called the Kronecker function. It's a quotient of Jacobi theta functions. So that's the Kronecker considers such a thing first. So this is also called Kronecker-Eisenstein series, for get Eisenstein into there, and it has been rediscovered many times since then, in particular by Don Zagier in the 1990s in the context of periods of modular forms. And yeah, and theta tau is odd Jacobi theta function. And right, so let me squeeze this in here. The key point is really now that this is a flat connection. Right.
Why don't use this holomorphic and then this dx by...
Thank you, that was my next remark, yeah. Right. So, okay, so maybe a slightly personal answer. So when I started off with elliptic multiple zeta values, I was very much reading Brown Levin and Levin-Racinet and also Kalak, Enriquez, Etinghoff. And yeah, it's not a quite a good answer. They didn't do it. So so this is, I think, how Brown Levin write down the connection. But you're absolutely right, the more natural thing would be, maybe if you're interested in periods and more algebraically minded, is to instead of the dr take a differential of the second kind. And no, I have to. Maybe the more precise answer to your question is that it's in fact, so if you want to be more algebraic, then you start with, let's say you don't have the, so you say you have the differential of the first kind here, 2 pi I d xi times b, but then instead you take a differential of the second kind, more precisely take the Weierstrass p function. This really corresponds to your x dx over y. On the Weierstrass model d xi. So, and you can start from this connection. Again, it's not going to be exactly the right thing, but you can make this into the right thing using also this Kronecker-Zagier function over there. And I mean, I haven't done this, but there's a PhD student of Decane who's done all that, showing that it really is that the Knizhnik Zamolodchikov Bernard connection defined by Levin and Racinet is really algebraic. And as a regular singular point at the zero section is particularly important, and it's on the archive. And I hope I'm not so good with numbers, but I think that the archive reference is 1710.07691. So you can read his account on how you do it algebraically. But in principle, it doesn't matter. So my point is that if you, so it does matter, but for what I do, for the period we get out at the end, it will not matter.
So is this connection still wrong?
Yeah, it's still not quite the right connection because you are, yeah. I mean,
It's flat, but it has, it's not algebraically gauge equivalent to something with a log singular.
yeah. So this is a double point, kind of, right? There's a double point, and you want to have a singular, regular singularity at the origin. Right? So, I mean, if you look at it chromologically, of course, everything is fine. But if you really want to look at the differential form, then it does just as a double point.
But I was trying small dimension. I was calculating monodromy. It was looking very nice.
Oh, great.
But,
Maybe we can talk about this. It sounds very interesting. So I didn't know that you were working also on this. But anyway, so you can do it, but I'm going to use that connection. And it's, for what I'm doing, it really doesn't make any real difference in the end. Okay. Okay. So we talked about the Knizhnik Zamolodchikov Bernard connection. Now I would like to talk about the issue of the base point. Here I'm going to be very brief. I'm just telling you the base point I work with. And the base point I work with, called B0, so again, it has to be tangential. And it will be plus, so you can, okay, two choices now only. Plus or minus 2 pi I to the minus 1 del psi. And if you're annoyed by the 2 pi I to the minus 1, the key point is that this is integral and has good reduction over spec z if you look at it on the Tate curve. So this is in the tangent space of the complete elliptic curve at 0, and this is somehow at the tangent space at 1, the Tate curve. And you see z is, of course, e to the 2 pi I psi, and this is why you have to have the 2 pi I to the minus 1 if you work on C modulo the lattice. And again, once we've found our correct base point, we want to take the monodromy, we have to regularize, so we take the regularized monodromy of our flat connection along homotopy classes of paths alpha and beta. Now they are going to be in, it's going to be like this, it's going to be paths from minus v0 to v0. What you get if you do this, so you have alpha and beta, you have two paths, and correspondingly you'll get two power series. You'll get a tuple power series A of tau and B of tau. Everything will depend on the modular parameter, and it's going to be still a formal power series in A and B, but the coefficients are now going to be holomorphic functions on the upper half plane. It's a direct product of two copies. And this is the elliptic KCB associator, which I think made a brief appearance in Decane's talk on modular inverters. But this is due to Enriquez. Okay, and okay, I'm telling the story slightly backwards with respect to the multiple zeta values. Multiple zeta values you can define without knowing what the Knizhnik Zamolodchikov connection is. That's no problem. Euler didn't know, I think. He just wrote down these series. Here, on the other hand, we know what the KZB associator is because we know what the KZB connection is, and we're going to define elliptic multiple zeta values in the following way by just taking coefficients of the elliptic KZB associator. So precisely, so star is just going to be a placeholder for either A or B, because I don't want to write everything twice. You just set EZ upper star take the Q span of, so this is now where the star comes in, so again, it's really a placeholder for A or B, and take the coefficients of all words in A and B. And it's going to be holomorphic functions on the upper half plane. And that's going to be called the, I will not prove this, but it's going to be a Q-algebra, in fact, because we're talking about iterated integrals. And it's going to be the Q-algebra of, to be precise, of star elliptic multiple zeta values and ZVs. Okay. Right. Okay, so far, what do we have? We have this connection, we've taken its monodromy, and we've taken coefficients. The natural question is, what are we really talking about here? So, concretely, what are elliptic multiple zeta values? And if you know how this monodromy business works, then of course you know they are going to be regularized iterated integrals on a once-punctured elliptic curve. This will qualify as an answer, and if you want to be more precise, what you can do is you can take this Kronecker-Zagier function, you can expand it in the second variable in eta, get a Laurent series in eta with a simple pole at eta equals 0, you can take the coefficients. And these are going to be your integrands. I'm saying this very quickly because I don't even want you to remember this, because the correct answer somehow will be, they're going to be iterated integrals, but not on the elliptic curve. But it turns out they're going to be iterated integrals on the upper half plane.
Excuse me, you are saying which multiple zeta value, but it's not a value, but it's a function, right?
Right, yeah, so I probably should call elliptic analogs of multiple zeta values, right? Then it's okay. Right, yeah. Yeah. So the emphasis does not lie in the value, but I understand that this can be confusing. Yeah. They're really functions of because you have many elliptic curves, right? So you would expect functions. Okay. Right, so they're going to be iterated integrals on the upper half plane. And okay, and the rest of this talk I'm going to try to make this more precise, and depending on how much time I have, we'll see how far we get. So I'll denote calligraphic i's. I'll let this be the Q-algebra, or the Q, well, it's a Q vector space a priori, but it's also Q-algebra, defined by iterated integrals of Eisenstein series, where I leave the lower integration domain, lower integration variable as variable, it's tau, it's going to vary, and I integrate all the way up to I infinity, but I have to be a bit careful here because what I will integrate over will not vanish at I infinity. And there's this, again, this business of tangential base points that I will not want to go into for now. So I learned this from Francis Brown's paper on multiple modular values, how you do it. And you can do it, and then you're taking iterated integrals of Eisenstein series, and the ki are greater or equal than 0, and n is also greater or equal than 0, and this is just a normalized Eisenstein series. Of weight 2k.
You say ki is greater than or equal to 0.
Right.
What would it be if it was 0?
Minus 1. Minus 1. For SL2Z. No, it's going to be minus 1, yeah. Convention. G0 minus 1.
So G2 is allowed?
Is allowed, yeah. It will play a minor role though. Yeah, it will play a minor role. So roughly speaking, it will only occur in single integrals. So you'll not have a proper iterated integral of many G2s somehow. or yeah. And so this is one part, and the other is telegraphic Z. That's going to be the Q-algebra of MZVs. And then I think that, so Enriquez was the first to realize this, I think, although it's, is that elliptic multiple zeta values, whether A or B, are going to be contained in iterated integrals of Eisenstein series, tensor over Q, with Z, and I think, yeah, you have to add 2 pi I here, otherwise it's going to be wrong. And, right, so really elliptic multiple zeta values are on the nose linear combinations of iterated integrals of Eisenstein series, viewed as functions of the endpoint tau, start point tau, with coefficients multiple zeta values. Let me give you some examples. So I'm going to put star equals B now, because there are some annoying subtleties. If you want to be really precise and not say anything wrong with the A MZVs, but I will skip that. So for example, 1 and also 2 pi I tau are elements in EZ. And you think of 2 pi I tau kind of as integral of G0. From tau to infinity. And I'll not explain this, but this is in some sense the depth 0 part of EMZVs. So this is depth 0. These are depth 0 EMZVs. If you look at them, they're precisely, for my choice of framing, they are the periods of the elliptic curve. They are what you get when you integrate this holomorphic differential along along the path A. And more interestingly, is if you look at the depth 1 part, this is somehow going to connect with I think with regulators. What you're getting is you're getting an odd Riemann zeta value, and you're getting some prefactor 2 pi I to the 2k minus 1 over 2k minus 2 factorial, and then you're getting an so-called Eichler integral of the Eisenstein series, G2k. And so I computed this thing, and then I found out that, I think he's not there, but Brown Levin has a 1998 Compositio paper where he computes special values of elliptic polylogarithms, so in the complex setting. And it was a bit surprising to me, but then of course not very surprising, that this is really precisely the special value, or one example of special value of Beilinson-Levin elliptic polylogarithms. Polylogarithm at the 0 section. So elliptic polylogarithms, they also depend on the psi in the elliptic curve, and you can evaluate them at 0, and you get this. All right. So, short remark for all people who are more interested in periods and less interested in families of periods. I mean, elliptic multiple zeta values are kind of functions depending on the parameter tau. But what is nice about them, if you specialize them to interesting points, to interesting tau, then you're getting interesting numbers. And the thing is the following. So if the elliptic curve you started with, punctured elliptic curve, if E tau is defined over a number field, then you can look at let me put it like this. So if you evaluate elliptic multiple zeta values at tau, at the same tau as the elliptic curve here, And this is going to be a subalgebra of the algebra of periods in the sense of Kontsevich and Zaghi, except that I don't know, there are two things where I don't think they're periods, but maybe someone in the audience does know better. You have to add tau, and you have to add the logarithm of the Dedekind eta function at tau. Perhaps. So remember, tau is the way I do things. Tau is not really so this is periods in the sense of Kontsevich Zaghi. So the way I define the periods of the elliptic curve, so tau is really a ratio of periods, right? So you take the integral of the holomorphic differential over one cycle, then you divide by the other cycle. I don't think that's a period in the Kontsevich-Zaghi sense. It's perhaps similar with the story whether you have to count 1 2 pi I as a period, 1 over 2 pi I as a period or not. And the logarithm of the eta function, this goes back to Jans Dienstra's remark, this has to do with the Eisenstein series G2. So if you integrate the Eisenstein series G2, you're getting log of eta, and then you have to worry about the value at, well, this. I would assume things are somewhat nicer if tau's addition is CM point, then at least this is a period, it's going to be an algebraic number. But I'm still not sure about this one. If anyone really knows, would be very happy to discuss with you.
You should be able to get rid of G2 up there. I mean,
should I?
Yeah.
Yeah. I could. Okay. Yeah. That's a bit of a nuisance. So, okay, maybe remark for the experts. So, I mean, you have to regularize here, and the cases in which you have to regularize are precisely the ones where you're getting the G2. So, somehow, if you have a divergent iterated integral on the once-punctured elliptic curve cooked up from this Knizhnik Zamolodchikov Bernard connection, it's precisely the case where you're getting a G2. So maybe there's a way of saying I only look at convergent. I don't know. But it's really only going to be the single integral of G2 that is going to matter here.
So that's still star equal to B?
No. Oh, sorry, star is either one. No. Star is either A or B. Sorry. Yeah, thank you. Works for both. Okay, I got like 5 more minutes. So let me wrap up. Okay, I want to talk about one more result, and for this I'm going to need to introduce a bit more notation. So, if k is greater or equal to 0, then we're going to define a derivation epsilon 2k of the free Lie algebra on A and D. That's the free Lie algebra. By the following formula. A is going to get mapped to the 2k adjoint action of A acting on B. You can also give an explicit formula for B. It's a bit lengthy. Let's be explicit. So you sum over all j greater or equal 0 less than k, and then minus 1 to the j times commutator bracket jth adjoint action of A acting on B, 2k minus first minus jth adjoint action of A acting on B. And they appeared in Decane's talk on Monday also. And in his in the setup of Matsumoto and also for Brown, these kind of encode the action of the relative completion of SL2Z on the once-punctured elliptic curve. Just to quickly connect with Decane's talk. And what are they going to do for us? It's going to be somehow related.
Damn. Just showing the shoulder.
we're almost there. Sorry about that. I came so close. Last board I erased. How that happens. Okay, before I tell you anything else, let me put Michael on the board back again. Okay, it's not hair but chair. Right. Okay.
It is hair.
If it was an E. Well, no. Okay, right, so we want to look at these derivations. And maybe I should say that to also give a bit of credit, I give a lot of credit. So I think Tsunogai was the first student of Yosutaka Ihara, first considered them in a Galois theoretic setting. But they've been rediscovered many times afterwards since then. And we're going to look at the Lie algebra. Little u is going to be the Lie algebra generated by the 2K inside all derivations. On the 3D algebra. And u prime is going to be the kernel of the projection onto epsilon 0. Going to be some Lie ideal. And then the theorem is that we have canonical isomorphisms of, so again, star is either A or B, and then, well, Z star, and so for technical reasons, we got to work modulo 2 pi I here. I'll comment on this after I've written down the theorem. So it's isomorphic to the universal enveloping algebra u prime graded dual tensor with multiple zeta values modulo zeta of 2. This is if star is equal to A. So this is why you have to be a bit more careful if you work with A elliptic multiple zeta values. And with B elliptic multiple zeta values, you're getting an isomorphism with the whole capital U, the whole universal enveloping algebra graded dual of the Lie algebra. And this is a star is equal to E. Okay, last remark. So you see we are working modulo 2 pi I here, so it's not messing up the weight grading. And we expect this is that this can be repaired, so we expect that.
So what's the element that's due to epsilon 0?
Tau. 2 by tau.
2 by tau.
Expect that this lifts that theorem is also true without having to pass modulo 2 pi I. So you don't want to quotient. But this is all we have. And very last remark. So this kind of tells you that elliptic multiple zeta values have an arithmetic component. This is the z over here, the multiple zeta value. So if you go to infinity, an elliptic multiple zeta value will degenerate to a multiple zeta value. And they have a geometric component, which is given by this Lie algebra U. And this, I think, kind of fits into, for example, in some sense, in the structure theory of mixed elliptic modes, Tsuta and Matsumoto, where you have a geometric fundamental group and an arithmetic fundamental group. And the whole thing is somehow a semi-direct product of the two, except that here we don't quite have, we don't really know the action. So in order to have a semi-direct product, somehow also Z would kind of coact on here, but that would coact on there. And we don't know how to do it Okay, that's all I wanted to say. Thank you for your attention.
So, questions? Well, seeing none, next talk is at 3 o'clock. Oh, no, go ahead.
So epsilon ZA is contained in epsilon ZB, right? EZA is contained in EZB, right?
EZ, this?
Yeah, this star is equal to A.
Yeah.
Is
Right, yeah, exactly. That's exactly right, yeah.
Were you asking a question? All right, then the next talk is at 3 o'clock.